A transistor, as far as we are concerned, is a switch. It has all sort of other useful properties, but for us, it is a digital switch. So here's how the symbol looks like. We have source over here. This is the ground. This is the controller. So this is what controls the flow of current. The current wants to go from the source to the ground, but the controller controls it and says if you could go or not. So essentially, if you have 0 over here, the current can't flow. But if you turn this on, you give a 1 to it, the current flows from source to ground. And you could also have the inverted ones as well. So like this guy. And so you could have, so this guy works completely opposite of the first one. When you give a 0, it actually turns on and the current can flow through it. But if you give a 1, the current can't flow. And now that you could put a lot of transistors on a single chip, what we could do is not create more and more complex structures. So before this, we just saw how you could use transistors to make switches, and you might be wondering, okay, so what? No, they had mechanical switches in those days as well. So how does this making an electronic switch make any difference? Well, the difference is once you put a lot of them together and create more complex structures, you could implement electronic logic. So let's see how to implement logic using transistors. What you see over here is something called as an AND gate. For an AND gate, the output is on only when both of its input are on. Let's see if that is true. Let's say you give 0 over here and 0 over here. So this transistor is off and this one is off as well. So the output at this point is 0, right? Let's say if you give 1 over here and 0 over here. So this 1 will cause this transistor to turn on, and this is 0, so this is off. So the output still can't reach, the voltage still can't reach the output over here. So it is still 0. Let's say if you turn this one on instead. This one is on, but this guy is still off. No, sorry. So let's say if you turn this one on instead. So this guy is on, but this one is still off. So the voltage still can't reach the output. This output will be 1 only when both of its input are 1. So this guy is on and the voltage can reach the output now. So this guy will be on now, 1. So my challenge to you is implement an OR function using transistors. So come up with a configuration just like we saw for the AND gate. Implement a similar configuration to have an output Q, which is function of A plus B. So here's how you would implement it. Instead of placing both the transistors in series, you would place them in parallel. So what would happen is even if one of these transistors turns on, the current can flow from the VDD to the output, and thus you would get a logic 1 over here if any one of this inputs turns on.